heren, ladies and gentlemen, geachte collega's, hier opnieuw. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. I hereby formally open this session and I welcome you all to the public defense of Akke Corporaal. Akke Corporaal has presented to the faculty her PhD thesis on the topic infrared interferometric characterization of second-generation protoplanetary disks, partial fulfillment of the requirements for obtaining the degree of PhD in science, astronomy, and astrophysics. She shall now publicly defend her PhD thesis. I will first introduce you to all the jury members who are here. We have, first, I will start on the left to make it more easy, Professor Jan Sundqvist from KU Leuven. Then we have Professor Denis de Frère, also from KU Leuven. Then we have colleague Marco Baas from UGent. We have online, we don't see him right now, Professor Rens Waters from Radboud University in Nijmegen. Professor Paola Pinilla from UCL was also part of the member, but she's not here today. And then I have two more colleagues to introduce you. These are the supervisors of Akke, Professor Hans van Winkel and Dr. Jacques Pluske. My name is Mieke de Kok. I'm professor also in the physics department, so I will act as a chair today. After the introduction of the jury members, and I invite them to take a seat right now because I will hand over the floor to Akke. Akke, you are invited to give a presentation of about 45 minutes about your work, and afterwards the examination committee will ask you questions and discuss your work with you. Okay. I now give you the floor.
Okay. First of all, welcome everyone, and welcome to this thesis event. Whether you are joining here in the room or somewhere somewhere around the world. I'm very happy to share with you this thesis, which I worked on for the past 4 years, which is titled Infrared Interferometric Characterization of Second-Generation Protoplanetary Disks. In the first part of this talk, I will focus on, I will explain the terms that are needed to understand the title of this thesis, and then I will highlight some of the results. Let me start close to home, planet Earth. It was once formed in a rotating disk of gas and dust. This rotating disk was formed around the young sun as a byproduct of the star formation phase. Some material of this disk was accreted onto the forming sun. At the same time, many processes in the disk were taking place. These grains have stuck together, and have in this way led to the formation of our solar system planets. The timescales at which these happened are long compared to human lifetimes, but short in astronomical terms. Our solar system planets must have formed within a few million years, after which the disk is dissipated. We could not have witnessed the evolution of this disk from its formation 4.5 billion years ago till what we see today. However, we can study our young stars that are now surrounded by such a rotating disk of gas and dust, and as such piece together what has likely happened and is happening in, from the assembly of the gas and dust in the disk to the formation of the planets. We know that under the right conditions, planet formation takes place in these disks. Therefore, we call these disks also protoplanetary disks. For such protoplanetary disks, we now have a good, we begin now to understand what processes are taking place that are both hindering and advancing planet formation. These processes range from growth processes to destruction processes to the transport of dust grains. Once the star in the center has accreted enough material and the core reaches temperatures high enough for nuclear fusion to take place, the star is born. This star is now on the main sequence. the longest and most stable stable phase in the life of a star. Our sun is currently at this stage. In this thesis, I focus on low to intermediate mass stars, which are sun-like stars with masses of 8 times the mass of the sun or lower. These stars run out of their core hydrogen on fuel, typically after a few billion years. The star expands, becomes a red giant, sheds its outer layers, and ionizes the circumsolar environment. What's left of the star is its bare core, which will become a white dwarf. In this thesis, I focus on a phase in between the red giant and the planetary nebula, which is called the post-asymptotic giant dot or post-AGB phase. The Sun will reach this phase in about 7.5 billion years from now. The exact evolution of the star depends on its mass and its composition. Another factor that is important in the life of stars, or at least in the late stages of evolution, is the effect of other stars. Many stars, and in fact half of the low to intermediate mass stars, are born in pairs. These stars can significantly differ in mass and thus in how fast they evolve. And we call such systems binary star systems, which are systems in which two stars are orbiting around the common center of mass. When the initially more massive star has evolved to the giant phases and it will evolve faster than the other star. When that star reaches the giant phases, there's more interaction, so the outer layers become generally looser, there are stellar rings, and this will spread to the material that is not so bound anymore. So mass transfer will take place, which we call binary interactions. A system which is the result of such binary interactions are post-AGB binary systems. These systems are the subject of this study. We now have a good understanding of the different building blocks, but they are still quite complex systems. And I will now walk you through the building blocks. We have a binary star system consisting of a post-AGB star and a main sequence star. These produce quite a lot of electromagnetic energy. The main sequence star is similar brightness as our sun, but the post-AGB star is 10,000 times brighter. The main sequence star is surrounded by an accretion disk from which bipolar jets or high-velocity outflows are originating. The system is then surrounded by a stable, rotating disk of gas and dust. This dusty disk has a radius of about 100 astronomical units, which is the same as 100 times the distance between our sun and the Earth. And there's also observational evidence that there is mass transfer between the circumbinary disk and the central stars. I focus in this thesis on the characterization of this dusty disk. The primary identifier of these disk-hosting systems are the spectral energy distributions, which we know from photometry. And I will walk you through this. From photometric observations, we measure the energy that is emitted by an object. And if we do this across the electromagnetic spectrum, we can build a so-called spectral energy distribution. And this gives actually the energy that is emitted over as function of the wavelength. An example of a spectral energy distribution for such a post-AGB binary system is shown here. The colored data points show the photometric data points, and the red curve shows the energy that the star emits. You can see that these photometric points are lying above what the star emits. So there's excess of energy that is not emitted by the star, but is actually emitted by the disk. This excess of energy starts in infrared wavelengths and continues all the way to millimeter wavelengths. This means that both hot and cold dust is present in the system, and that's why we know there is a disk in the system. The presence of this disk is strongly linked to the binarity of the system as well. Previous studies have already characterized many of the disk properties and have shown that these circumbinary disks around old stars are very similar to the protoplanetary disk around young stars. Both kinds of systems have similar infrared excesses or similar excesses of energy, starting from the infrared to millimeter wavelengths. The disks are stably rotating, There are signs of disk grain growth. For post-ACB disks, we know that there are large grain present in the disk, at least up to millimeter sizes. For protoplanetary disks, we have a few more advanced indications of disk grain growth. And disk masses are on the order of 10 to the minus 3 or 1,000th of a solar mass, which is actually quite heavy, which is also in a similar range for protoplanetary disks and post-ACB disks. Because of these similarities, we think there is a universality between the disk and the disk evolution. And as given the significance, the surprising similarities between these two kinds of disks, we also call these post-ACB disks second generation protoplanetary disks, as I did for the last part of this title of the thesis. But there are also a couple of important differences. First, the host star luminosity of a post-ACB star of a post-ACB disk is way more luminous. Second, there are differences in the formation processes, namely protoplanetary disks are a byproduct of the star formation process, while post-ACB disks are formed as a result of a poorly understood binary interaction phase. Third, the disk lifetimes of post-ACB stars are only 100,000 years, which is a factor of 10 or more shorter than the disk lifetimes of protoplanetary disks. And fourth, the environments are very different. Star formation takes place in very crowded regions, meaning that the evolution of protoplanetary disks is governed by external processes. But only post-ACB disks are quite old and not in such crowded regions anymore. But they could still have surviving remnants of first-generation planets that are created in the star formation process in the protoplanetary disk phase. And this could actually affect the structure and evolution of this post-ACB binaries. So what is now the importance of studying these disks? Historically, these disks were mainly studied to understand how the circle binary disk influences the evolution of the stars and vice versa. This is because we know that these post-ACB binary systems are binary interaction products, but this binary interaction is very poorly understood. The disk, there is evidence that there is interaction between the disk and the central stars, which can alter actually the properties of the stars and thus their further evolution. We can also study these systems from a planet formation perspective, as these are so similar to protoplanetary disks around young stars. These systems can be used as an excellent laboratory to study planet formation mechanisms, as we have a very different parameter space available than for young stars. The study can bring significant implications on the initial stages of planet formation around both young and old stars. The goal of this thesis was to make a deep comparison between circumbinary disks around old post-ACB binary systems and protoplanetary disks around young stars. To do so, I focus on the characterization of the inner disk regions. The reason for this is that in these regions we expect many processes to take place. Thus, in these regions is likely the base material for planet formation processes. I used a technique called infrared interferometry, which probes the dust residing in these very inner regions of the disk. And this also explains the first part of the title of this thesis. The radii that we probe are on the order of 10 astronomical units or so. Despite their huge sizes for human standards, astrophysical objects are so far away that we need incredibly large telescopes to observe them in detail. The angular resolution of the telescope depends on the observing wavelength of the instruments and the diameter of the primary mirror of the telescope. So this implies that with a larger collecting area, we can see more details. If you now get one telescope with a diameter of 8 meters, equipped with an infrared instrument and pointed to the moon, we would be able to see details with the sizes of approximately the atomium in Brussels. With interferometry, we can combine the light of different telescopes And as such, actually, we are not limited anymore by the diameter of the telescope itself, but what we are limited to is the projected distance, or we call this also a baseline, between the telescopes. So we've taken up to 2 telescopes, separating them by 130 meters. We would be able, equipped again with an infrared instrument, we would be able to see sizes or details with the structure with the size of a cargo bag on the moon. If you now apply this to our post-HB binary system, which is located 80 billion times farther away, we would be able to see structures of the size of an astronomical unit. In this case, I use instruments that are on the Very Large Telescope Interferometer, or VLTI, which is located in the Atacama Desert in Chile. This facility has infrared interferometric instruments, and these instruments combine the lights of either the 4 stationary telescopes or the 4 movable telescopes. These 4 telescopes can be moved along the rails that you can see here, and actually, they can only be there at predefined stations or configurations. So with interferometry, we do not get the image of the star directly, but I need to explain the steps that we need to take to obtain astrophysical information of this system. So let's go back to our star-based system. Imagine that we can observe it, and we collect the lights of the system by the 4 telescopes of the VLTI. The light beams will pass through a set of mirror trains to equalize the distance the light is traveled. The light beams are then combined and they interfere on the detector. This will give an interference pattern or interference fringes. Each component of the system that we observe produces its own fringe packets. We can calculate the height of the fringes or the amplitude of the fringes, and also the phase, which is the position of the peak of the fringe pattern. And the interferometric observable are a measure of this amplitude and the phase. In interferometry, we will sample not directly in the image plane, but we will sample in a so-called spatial frequency plane, so in a frequency plane. So sample the interferometric observables. And these interferometric observables are related to the true intensity distribution of the objects by a mathematical relation called the Fourier transform. The challenge of interferometry is to then sample the Fourier plane as much as possible. With each baseline and with each observing wavelength, we get a point in the spatial frequency plane and progressively builds the visibility curves. Because the interferometric observables that I was talking about are actually called visibilities, which is a complex number. In this way, we can get so the advantage of observing with the 4 telescopes is also that we probe different baselines simultaneously. We probe larger and smaller baselines, where the larger baselines probe the smaller scales, and the smallest baselines probe the larger scales. If we sample the spatial frequency plane as much as very, very well, then we can, in principle, invert the Fourier transform and retrieve the image of the object by image reconstruction. If this is not the case, we can still get a good understanding of the astrophysical objects, because we can, in principle, model the interferometric observables and as such retain the information. In this thesis, I focused on modeling the visibility or the amplitude of the visibility of the invisibility fringes using modeling efforts. What we typically measure is actually not the visibility amplitude, but the square of the visibility, because we get the intensity of the fringes. The visibility encodes information such as the relative brightnesses of the objects, the sizes, and the shapes. The visibility is a number between 0 and 1, where 1 means that we have an unresolved point source, meaning that the size of this source is way smaller than the angular resolution that is probed. A visibility of 0 means that we have a very extended emission, where the size of this object is much larger than the angular resolutions that are probed, or outside the field of view of the interferometer. If you observe a ring, which we do in our started system, so we actually model the disk as a ring with a certain width, then we get a visibility curve that looks like this. The shape of which is a so-called Bessel function. If we now observe our started system, we get a visibility curve that looks like this. You can see that there's an offset between the last one that I showed and this one, meaning that this is just a linear combination between the star and the disk, both in the image plane and in the spatial frequency plane. Before I continue to the main results of this thesis, I need to introduce some terms related to the disk structure. So I already introduced you to the spectral energy distributions, which are the main indicators of the disk systems, because there is extra emission on top of what the star produces, starting in the infrared and continues up to millimeter wavelengths. So recently, a catalog of the 85 post-HB binary systems in our own Milky Way was built, and we looked at the different strengths of the near-infrared and mid-infrared excesses, and as such grouped together all the disks. The majority of the disks have an infrared excess as an excess of energy that starts in the near-infrared. These are grouped together as category 1 objects. These disks are called full disks, as they start, the dust starts close to the star, it's very hot, and then continues radially outwards. Some disks actually have a lack of, some systems have a lack of near-infrared excesses, which indicates that there is there are cavity in the disk. This starts farther out in these systems. These are grouped together in category 2 and 3 systems, where the difference between the two is their strength of the mid-infrared excess. In the category 2, on this side, we see that there is a strong mid-infrared excess in the spectral energy distribution. At this point, we find similar shapes in the spectral energy distribution of young stars. So we also adopt the term of the young star object community, and these are then the transition disks. So these are disks with an inner cavity and an inner distribution. Okay. Category 3 objects have a milder mid-infrared excess, and therefore we think that this category represents objects that have a full disk and objects that have a transition disk. And what we now can probe with infrared interferometric techniques are scales that are different for both full disk and transition disks. So the VLTI is equipped with both near-infrared and mid-infrared instruments, and we need near-infrared interferometry to probe the dust inner ring, the hot dust of the full disks, while we need mid-infrared to probe deeper in these disks. For the transition disks, we do not probe the disk at all with near-infrared interferometry, simply because they do not emit at these wavelengths. Then we need mid-infrared interferometry to probe the dust inner ring. So this brings me to the key results of this thesis, starting first with the inner ring structure of a post-HB disk. So we have a very rich data set for one very bright post-HB binary system. And we know that this system hosts a full disk. The disk starts just at the dust sublimation radius. We have data for these instruments taken with the 3 current instruments on the VLTI, Pioneer, Gravity, and Matisse. Pioneer, Gravity are near-infrared instruments. Matisse is a mid-infrared instrument. In the wavelength range in which these instruments are operating, the spectral energy distribution shifts from a star-dominated regime in the near-infrared to a disk-dominated regime in the mid-infrared. First, we modeled these systems with geometries that can be constructed analytically. Here I show the data in blue and the best fitting models in orange. Below I show the images of the best fitting models. We found that the near-infrared data were best fitted with a single temperature ring model, while the mid-infrared data were best fitted with a multi-ring temperature gradient model. And below, if you look at the images, you can see that these models have a different geometry. This means that we have a difference in geometry between the near-infrared data, which probes the disk inner rim, and the mid-infrared data, which probes beyond the disk inner rim, deeper in the disk. If we combine this with what we know from the spectral energy distribution, namely that around a third of the energy that is emitted by the post-ACB star is captured by the disk, which would mean that the disk needs to be vertically extended somewhere, we concluded that the vertical extension should be at the disk inner rim. Moreover, and actually we call this vertical extension a puffed up rim. Moreover, if you look at the geometry of the best fitting model in the near-infrared, namely the first two images, we can conclude that this inner rim is not only vertically extended, but also rounded. Then we went on to do a more physical modeling of this same post-ACB binary disk with the same model, but now we used more physical models, radiator transfer models, so numerical solvers to reproduce the interferometric observables. We aim to build a physical model that reproduces both the photometric and the rich infrared interferometric data set simultaneously. By doing this, we can get a good understanding of the disk parameters of this typical full disk around the post-ACB binary system. So, modeling, giving all the models of such models, computing all these is quite computationally expensive, and therefore we developed a strategy to limit the computational time. Our strategy provides us not with one good model that fits all models all data perfectly, but it rather gives us a family of models that reproduces the data. Here I show the results of one of those best fitting models, where I show the data in gray and the best fitting model in orange. And below I show the images of these disks, indicating that again, that's in the mid-infrared we are probing deeper into the disk than in the near-infrared. So our modeling did not provide us with only one good model, but with a family of models, but we can still get a good physical understanding of the disk parameters. Here I show the 7 extensively explored disk parameters and the distribution. And I want you to focus here on the orange diamonds, which represents the family of the distribution of the family of the best fitting models. I interconnected them for clarity. From the slopes of these lines, you can see which disk parameters are strongly preferred over other disk parameters. For example, the third column, you can see that which is the scale height at the disk inner rim. You can see that H naught value of 1.40 astronomical units, which means that the vertical extent of the disk inner rim is 1.40 astronomical units, is strongly preferred over all other disk parameters. Similarly, we know that beta is probably small, so this is a flaring parameter. So starting from the disk inner rim up to the outer regions, it's strong, but not that strong. It's still a flaring disk. Disk masses are preferred to be smaller as well, but still 10 to the minus 3, which is still quite a lot. Grain size distributions, the grain sizes are given by the distribution given by a power law, with a power law index that prefers smaller values, meaning that there are more large grains, and especially in the inner disk regions, given the interferometric observations. And we also tested whether there could be an extra source or other disk composition available, namely metallic iron, and we think that this is not the case. All in all, oh wait, this is a different one, sorry. All in all, we could constrain 5 of the 7 disk parameters very well with this very rich data set. And we concluded that the disk is flared, is quite massive, has a strong degree of dust settling, and there are large grains present in these regions. Oh well, we could constrain what a typical full disk around the post-HTTP binary system looks like, but we could not reproduce all observations very well. And especially what we also see in other modeling efforts of post-HTTP binary systems, we systematically overestimate the visibility data at the shortest baselines, which mean the largest scales. There's some large-scale emission missing, and we wanted to see if we could understand where this is coming from. So here again, I zoom now into the shortest baseline data, showing in dark gray the range of spared visibilities of the family of best fitting models, showing again that we are systematically overestimating the visibilities compared to what we see in the data. If we now add an extra component, we can go down to the light gray, which means we can probe in the similar ranges as the data. The temperature of this component points towards a mixed origin between photons coming from the disk inner rim, so which is on temperature of around 1500 Kelvin or so, and the luminous post-HGB star, which is on the order of 7000 Kelvin or so. So in future modeling efforts, we actually need to take into account this extra component, and we need to specify we need to understand the geometry as well. This brings me to the third result, which features the transition disk. We initiated an observing program with the new VLTI Matisse instrument. Matisse is a mid-infrared imager that combines the light of the 4 different telescopes. And we observed 11 post-HTTP binary systems, 5 of which are category 1 objects, which means that they have a strong near-infrared access in the spectral energy distribution, and 6 of these systems are category 2 or 3 objects, which means they have a lack of near-infrared access in the spectral energy distribution. We now aim to resolve this emission with the Matisse instrument, and we mainly aim to estimate the radius where the dust actually starts. So for the category 1 objects, we would expect the dust inner rim to be located close to the star and start at the dust sublimation radius. For the other objects, we expect the dust to be several times larger than the sublimation radius, and the starts farther out and is less hot. So with Matisse, we can now resolve these predictions, and these are the results. Here I show the radius at which this starts as a relative to the dust sublimation radius for 11 post-HTTP binary systems that we studied. The gray shaded area indicates the one-to-one line, where the dust, which is corresponding to the radius at which the dust starts, if this corresponds to the dust sublimation radius. For the category 1 objects, we indeed see that the inner rims are located at the sublimation radius, and therefore they are indeed full disks. For the category 2 and 3 objects that are probed in this study, we found that there are actually cavities in the inner disk distribution. The radius at which the dust starts is several times larger than the sublimation radius. So this confirms that there are indeed transition disks around all stars. This brings me back to the table that I've shown in the beginning, because this thesis, with these results of these works, we can extend the similarities between protoplanetary disks around young stars and post-HGB disks around old stars. In particular, with the multi-wavelength interferometric study that we did, we found that there are indications of the presence of large grains in the inner disk regions. We found similar dust masses of 10⁻³ times the mass of our Sun, as was previously found as well. we found that the dust in the rim is puffed up and rounded, and the disk is flared and has a strong degree of dust settling towards in a vertical direction. Moreover, with our VLTI Matisse observing campaign in the mid-infrared wavelengths, we could confirm that there are some disks that have a large cavity in this distribution. So there are transition disks around all stars as well. So in summary, we could contribute to, with these thesis, we contributed to the physical understanding of the circumbinary disks around positive binary systems. And we could quantify further the similarities between protoplanetary disks around young stars and positive binary disks around circumbinary disks around positive stars around old stars. But we also raised new questions, and we are far from a clear understanding of these of the physics happening in the circumbinary disk around all stars. So here I list some ideas for future studies, or actually that we should again investigate in the near future. First, in these studies, in these works till now, we neglected the influence of the main sequence star and actually also the position of the different stars. Our systems are modeled as axisymmetric disks, but as you can see from this image reconstruction of the same typical full disk around the positive binary system, it's quite asymmetric. This is an image reconstruction of the inner disk regions. Actually, we have a time series for these objects. So the first step would be to model this time series effects and to understand interactions that are happening between the circumbinary disk and the central stars. Furthermore, we plan to do a detailed characterization of the inner disk regions of full disk hosting systems. If the near-infrared interferometric data that is available now for a handful of these disks, we can characterize the similarities and differences between the whole sample, and therefore understand the physical processes of a larger sample. With the recent confirmation of transition disks, there are a lot of open questions, recent open questions, and in near future studies, we aim to progress on the understanding of the structure, evolution, and the origin of the transition disks. On the observational side, we would like to also probe the global disk structure. And this can be done using high-angle resolution observations in the sub-millimeter ordinary radio wavelengths. For this, the ALMA interferometer would be very useful, which is now around for around 10 years. And with ALMA, we can probe the global disk structure. And as such, piece together, if you combine the near-infrared data that we have in this probe in this study with the ALMA observations for both transition disks and full disks, we can get a complete understanding of the structure. In the foreseeable future, we also expect to open up to the characterization of circumbinary disks in other environments. In particular, the MATIS instrument on the extremely large telescope, which is now built in Chile, is now under construction and will hopefully be operational in 5 years. We expect not only to probe circumbinary disks in our own galaxy, but also those in companion galaxies of our Milky Way. So day by day, we can actually get new information to solve a piece in this large puzzle. Thank you.
Thank you, Akke. And I turn to the questions of the exam committee, and I would like to hand over the first questions to Professor Elsewaard from Nijmegen. Is he still online? areas. Okay. Please.
Yes, you hear me?
Yes, we hear you.
Perfect. Okay. First of all, I would like to apologize for the fact that I can't be there in person on this very important day for everybody there. But I hope that through this connection I can make up to that. And then, dear candidates, I would like to congratulate you with a very nice thesis that you've written with some very important results on a topic that is really very dear to me. And which covers the disks around all stars that seem to have a second generation of planet formation ongoing. And I'm glad that you put this really on the front page of your thesis so that nobody has to doubt anymore that this is actually what's going on. And I think your thesis is adding a very important piece of evidence to prove that this is actually the case. And of course, that's very exciting to think about as a second generation of planets being formed there. I also would like to thank you for these very nice introductory chapters 1, 2, and 3. I think that is very readable and offers a very good introduction to the topic for people who want to get into this and want to study these further. And also, last, and then I'll stop with the compliments and dive into the questions. I would also like to congratulate you with the fact that you, I think, are one of the first, maybe the first, to combine all of the instruments on the field T interferometer for a parameter study. I think that's a very big achievement. I think you beat all the other teams to that. So that's a great achievement. Okay, good. So now for the question, and of course I'm going to jump to chapter 7 immediately because you have this very nice table that we also discussed during your first defense, the results after your thesis compared to before your thesis, and I think that's a very important step forward. Nevertheless, I think what you have in that table are very interesting differences between disks around young stars and disks around evolved stars, and I would like to take you on that route a bit. And discuss these differences and what they might imply. And first of all, I think an important difference is, in fact, the lifetime of the disks. In the young stars, disks are there for a few million years, and you have in your table that these disks around evolved stars are only there for about 10.5 years or so. So that opens the question about the timescale for planet formation, which you talk about in your thesis. But I wonder whether you might be a bit too pessimistic, because there is also the phase of the disk formation phase. And I could imagine that this disk builds up slowly and collects solid material from which planets could be formed. So aren't you maybe too pessimistic in comparing the disk lifetimes of these two classes, also keeping in mind that the few million years that people are quoting for young stars is really the timescale for disk dissipation?
Yes, so to comment on that, yeah, maybe actually. There's for everyone, we actually have, actually, the timescales of planet formation are becoming we think actually that is now happening in shorter timescales than what we did, I don't know, 5 years ago or something. So in the past years, people have figured out that actually planet formation is happening quite fast and can actually be 10 to the 5 years. I don't know what they take into account if this is from the starting from the micro-sized grains already, that these grains are there in the disk, or if they, so I don't know where they actually start when computing this kind of the formation timescales. But yeah, it's true. But 10 to the 5 years is also limited by the post-HV phase itself. So actually, more massive stars have shorter post-HV phases, and therefore, this is actually more on the higher mass stars as well. So they can also be there for a shorter lifetime. This is a side track as well. I think it would be useful to collaborate more with the young star object community to see if this is too pessimistic or not. Because one of the things in post-HV binary is also that there could be remnants or first-generation planets there. This could actually also get some pressure bumps or pressure traps pressure bumps already in the disk earlier on than in protoplanetary disk around young stars.
Yeah, thank you. I think, well, there are two things to this. It's the beginning and the end. And so I think you might be too pessimistic in the beginning because the disk has to build up. And that could happen over an extended period of time. The binary evolution of the HB star that starts to lose mass into the circumbinary disk. So in that period, you could store more and more material, solid material, in the disk. Don't you think so?
Yeah, probably. There's this formation certainly around HV stars as well, and in the winds. So yeah, we do not count that stage yet. Indeed, that's true. That's a good point. We do not take that into account the time that this can already form in the winds of HV stars, or yeah.
And then on the other end, so yes, I think I agree with you that there's room for some study there. But also on the other end, you have this 10 to 5 years as the post-HGB period. But do you think that the disk is completely gone when the star becomes a white dwarf? You still have the main sequence star sitting there in the binary system that provides the luminosity of typically one solar luminosity star. So what happens?
Yes, it's so if the star heats up too much, it can it will also be high energy photons coming from the star. This can photo evaporate from the inside out the disk more. So I don't think we will see. So there will still be, of course, this material left after the post-HGB phase, but if we can really see a dusty disk with dust and gas inside, it will probably. I think it will photo evaporate away quicker because of the high energy photons that the star will produce.
Yes, I think that that's a very important difference between the two classes of objects. So I think, yeah, these high energy photons might be doing not so good for extended planet formation. If I may, can I ask a second question?
Yes, sure.
Okay, thank you. Yeah, so along those same lines, I thought it might be interesting to look at the chemistry of the planets that keep forming in those disks, because in young stars, material comes from molecular cloud, and we think that the chemistry is set by what happens in molecular cloud as that gas and dust and ice enters the planet-forming regions and then enters on the star, and then of course also feeds the planet formation process. But your disks are formed by gas and dust, which is leaving the star, so it's hot initially, and then it gets into this disk, and dust condenses into it, and so then it slowly cools down. So that's quite a different route for the material to enter into that disk. And then I thought a bit of code. Can we maybe from existing data see a bit about the difference in chemistry? And based on the results that actually one of your predecessors, Cleo Heeland, published in her thesis about the chemistry of the disk, I looked at her thesis, and she actually discovered a lot of carbon dioxide in your disks. And if we compare that to the chemistry that we see in planet-forming disks around young stars, so from the Spitzer Observatory, but now also from the James Webb Space Telescope, we see a lot of C2H2 and HCN. And I also know from the studies of your supervisor, Hans Winkel, that carbon and sulfur enter onto the central star. So they are apparently not part of the solid reservoir from which planets form. So with all these differences in the chemistry, can you speculate maybe a bit about what could be different in the chemistry of the planets that form in your disks compared to the planets that form in disks around young stars?
So first of all, I'm not an expert in chemistry at all, so this is really speculative. First of all, the young stars that we study now are more enriched in material, so have more metals in their from the molecular clouds which they formed already. Then those because they are forming now and not like billions of years ago. So there would be already a difference in chemistry, and the circumbinaries for positive binaries are created from the atmosphere of the involved star. So this has undergone a lot of processes already, such as the chemistry that Rens is talking about. So we have, of course, a different chemistry. So that's a bit to explain this. So could the planet, so yeah, it depends. I guess I'm really not an expert. So all these difference in chemistry. So we have oxygen-rich gas. So almost no carbon. So it would be very different, I guess, than what we see on Earth as well, because of carbon-based life. So yeah, the planets themselves in their atmospheres would be very different. And yeah, I'm not a very good expert in this to have an idea on what we could maybe observe or not, and how maybe you were referring to, maybe we can see later on in the stages if this is a first or second generation planet. Is this what you are referring to, or?
Well, that would be, of course, super exciting to try to do observationally, but that might be a challenge because of the distance to these objects and the fact that we first need to find planets around those objects in the first place. But I think it's an interesting thing maybe to add to your table of future work to think about, what kind of differences in these planet compositions, right? And how much carbon would be in those planets, or how much sulfur or zinc or any of the other chemicals would you expect to be in those planets compared to what you would have around the planet forming around a young star?
Yes, it's a good point. We should really work on this. But we need to first have the chemical models, I would say, to do this. We need to perform chemical modeling.
Yep. Thank you very much for this very nice exchange of thought. Thank you, Chair, and I give the floor back to you.
Thank you, Professor Marx. The next who gets the microphone is Professor Martin Maassen.
Thank you. I'd like to also congratulate you. It was a very nice thesis to read. I'm not very experienced in things so small as individual stars or binaries. It's the same thing. So your first chapters were extremely nice to read and to bring me into this world. So congratulations on that. What I also liked is your modeling approach, because I'm more of the modeling side. And I really like that first you did this modeling with individual analytical components and then moved on to real physical modeling. I think that was really nice. And my first question is also on that topic. Is your rate of transfer modeling is quite, it gives a very good fit. It's not perfect, but it's a very nice fit. I was a bit surprised that these were actually of the first fits of that nature, while in the protoplanetary community, this has been done for a long time. Can you explain what is stopping you or and your colleagues from doing that on a larger scale and doing extensive modeling of all topics? Is that just a question of manpower or a limited set of objects that you can model?
So the radiated transfer modeling, of course, is already done before with binary data and also MIDI data, which is decommissioned two-beam combiner on the VLTI with mid-infrared as well. So this was not the first of that kind that we only did modeling now in during my PhD. The Matisse instrument is quite new. It's only there since, available from the community since 2019. So we actually do not have a lot of Matisse data, and actually the data that was presented in this thesis was once one of the first Matisse data as well, because it was taken in the science verification phase, which is a phase in which instruments are generally tested, etc., based on the performance. So this was, in that sense, doing this from all the way from the H band to the K band. This was one of the first indeed. And also, since it was only available since 1919, I don't think actually there's currently another radiation transfer model that's works with the Matisse data and produces it with radiation transfer models, because there's just not a lot of Matisse data around yet. With MIDI, yes, there are indeed with the A-sense, combining this with MIDI, which was a mid-infrared interferometer as well. There are also in the post-HCV there's a study done, I think 6 years ago, with different systems as well. So, but then the gravity instrument was also not operating or not giving a lot of data yet. So, with these second generation instruments on the VLTI, and we can do really this multi-wavelength study for one of the first time. And yes, we are a very small research community. Not many people working on these disks, so it's also a manpower thing. But we have now data, both with NDAs in the near infrared, and for some also a bit more to the near and mid infrared, that we can now actually model.
Good. In your thesis, you mentioned, I like the comparison between the old stars and young stars disks. And you mentioned that there are three main differences. One is the formation history, you have the time scales, and you have the luminosity. Which of these dominates the differences? Can you...
Yeah, so this really depends on what you want to study. And for me, I think the time scales are the most interesting difference, because as Andreas also already asked, it's about the time scale of planet formation, and yeah, I am really interested in that. And to see, because it has effect on both the young stars and the old stars. So if we can constrain the life of the planet formation timescales, it would have implications for both kinds of disks. The luminosities are also important because it gives also a different gravity. So that actually can push the higher luminosity pushes the disk in a radius far away, which is not in any case really a problem. But it also gives more radiation pressure on the grains in the disk, which pushes the smaller grains. Yeah, it doesn't push them out apparently, because we see still the small grains, but the pressure on it is still high. So that effect is in physical terms important to understand.
Can I ask one more? Please. In the field that I'm working, the whole community is now all James Webb, and that is not for your disks apparently. Can you say to us, is that because it doesn't probe the right scales, or is there a reason why James Webb is less useful here or so? Or?
So it's not less useful actually. So I didn't include it in this presentation. It's several times in the thesis actually that we need James Webb to probe the scales. We can study actually this also with also to Nancy's question. We can study the mineralogy of the discrete JWC as well. You can see if there is gas present in the inner disk regions as well. But of course, the observational time of JWC is limited, and everyone wants to have data because it's just around. So for now, we don't have the time yet for JWC observations.
Thank you very much.
Thank you, Professor Hall. And we turn to one of our Cardone colleagues, Professor Bottet.
Thank you. Congratulations on your excellent presentation, and excellent thesis. So I'm not an expert, as you know, in PhD stars, but I really learned a lot by reading your first chapter. It's really recent. And I also would like to congratulate you on the modeling part and the data analysis part. I know it's really difficult to do analysis of interconnection data, even if you have a single point. And you did a fantastic job with these three instruments, many data points, and also complex astrophysical scene where you have binaries, you have the disk with multiple components. So it's really a huge amount of work that you have done. I'd like to congratulate you for that. I also would like to join Professor Hans Water about the comment about the three instruments. I think I'm the first to publish a paper using data from the tree instrument from the VLTI, and that's also a really big achievement, especially for new instruments like Matisse, where there are a lot of problems when you start producing data from the VLTI instrument. So just to say that there is a lot of work behind this data reduction effort and modeling effort, and it's explained in your thesis manuscript as well. I have two questions. The first question is about the path for the future investigation of the subject is to observe more inner disks, right? I was wondering with the VLTI, what is the main limitation? Is it the angular resolution that is not large and big enough, small enough for resolving the inner disk of more AGB stars, or is it the limiting magnitude? And would graph format, for instance, help to increase the sample of these kind of objects?
So so this is a question both on so I was mainly involved in the observer proposals for the transition disk, because these were then indicated based on the spectral energy distributions, and we wanted to resolve them with Matisse. For them, we're really observing all the limits. So this is really on the brightness limits, and we actually observe them with graph formats, which is for the people here. This is just we combine we take data with the Matisse instruments, and we use the gravity fringe tracker to stabilize basically the fringes, so that we can go to smaller. Well, we can actually go to fainted targets. So we use this this mode already in observations, and we were still on the limits for these systems. For other systems, well, we would like to, for systems that we can do, and actually all the full disks all the full disks, many of the disks that we can probe with interferometry, because they also should be in the southern hemisphere, are bright enough actually for Matisse and also with graph formats. And then, yeah, it's just also a thing to get the time on the telescope, of course. So we didn't try to do a large survey yet. That would be one of the first, that would be one of the main near future work as well, to do a survey on the Matisse disk for full disks as well, and do a multi-wavelength study on on the sub-performance. You also have pioneer organism observations.
Is it more difficult with Matisse than gravity to be within the magnitude limit, or?
For these disks, yes, because for the transition disks, yes. Oh no, well, for the transition disk, we need to have Matisse for observing the disk, because with gravity we will not resolve the disk; it will only get to the binary, because it's okay, but in the near infrared, and there's a lack of near infrared access, so there's no emission at these wavelengths. So for these disks, yes, there is only emission in L and bands, and well, we can observe these systems with gravity, which is also on the most. Actually, if we do this, then we also need the most. They're just not bright enough, so we also for the binary we already need the most sensitive mode as well. For the full disks, this is not really a problem. Actually, we just need to have a good science case and get the observing program committee or the distributed period, or the people who are in the community excited to give time on the telescopes.
Thank you. So I have a second question about this visibility excess that you have in your model at small baselines. This is something that is really interesting. Do you know if this is something they saw also in the young stellar object community, and how did they solve this issue?
Yeah, so this is also seen in the young stellar object community. That's way less. So there's way less emission, overresolved emission, or more extended emission in protoplanetary disks, especially with pioneer surveys that we done as well. I don't know. Just so that I cannot see the mouse. No. I don't see. Sorry, can you repeat?
So you were saying that this deficit of visibility is something we see also in the wider community, but less.
Yes. So what they solve is multiple routes, but they model that the radiation transfer goes as well with like a halo somewhere around it, or emission coming from the inner regions, which are actually very different because of other processes happening around these stars, which is not happening around our stars, such as the presence of high energy photons, etc. So yeah, we can assume that there is a halo around as well, but where is that still coming from? So we try to solve. It can also be solved by just the difference in geometry of the disk, and we try to do this in our modeling efforts. And well, we could solve for around half of the oversolved emission that was previously found, but not for all of it. We still have this extent of emission. So I don't think this is already done, and as far as I know, this is not yet done in the Youngstar community for these multi-wavelengths. So we see it in HKNL, and as far as I know, this has been shown in H for sure in the Youngstar community, but I'm not sure about the other wavelengths as well and how they will solve that.
Okay, thank you very much. No more questions for you?
And speak on it, so good.
Thank you very much, and thank you, Akke, for the presentation today. And I also echo the others here in the room and congratulating on your thesis. It's a very nice piece of work, and also, as has been said before, a very well written thesis, which was appreciated. Now, I'd like to continue the discussion on the timescales, actually, as has been taken up before. And you quote this roughly 10 to 5 years, right, for the lifetime of this. So I was just wondering, where is evidence for that? That's roughly 10 to the 5 years. Is it purely evolutionary, or are there also other purely evolutionary? So then that leads me to the question, I mean, where do you find these systems really? And the reason for the time scale there is that would there be a possibility to do some sort of basic number counting as well? Because if they live longer, there should be more of that. Or is that out of the reach? So first, I mean, where do you find them? Do you find them all over the place in Milky Way and other galaxies, or situated here and there? Or, and could you do numbers of this?
Yeah, so we know of 85 systems in our own galaxy, and we also know that these systems are in the large and small Magellanic Clouds, so the companion galaxies of our own Milky Way. Then from the large and small Magellanic Clouds, we know that there are roughly 200 of these kind of disks based on photometric observations, based on and then you can cross-match between catalogs and see these kind of systems.
And do you think is that consistent generally? Would you expect with this type of lifetime that you would assume that if they're around 10 to 5 years, but if they're around 10 to 6 years, should there be more, less found by now? If you were to speculate.
Yeah, so 10 to the 5 years is really for the the smaller mass post HB binary systems, or post RGB as well. This could there be more? I think this is a rough estimate already, given that the systems that we know of are that we studied best are located in our own galaxy. We don't know the distances, so we cannot really constrain exactly in which evolutionary states they are. We cannot pinpoint them on the diagram that we use to categorize our stars, because we do not know exactly the distance For the LMC and SMC, I think we have a quite good well, I think this is easier to pinpoint where they are in their life and get the number correct. Do we expect more or less? So these are all farther away in our, well, all relatively close by in our Milky Way, on the order of a kiloparsec or something, which is 3,500 years, I think. But it's still, we are 8 times that distance located from our, well, from the center of our own galaxy. So in our own galaxy, we expect to have way more. If this is observable, yeah, then I don't know.
Yeah, thank you. And then we can move down in time scales a little bit, because we discussed the radiative transfer model, right? And you also mentioned the possibility of doing time series observations. But when you look at the complexity of this, shouldn't they also be very dynamical systems? In the sense that they are time-dependent dynamical systems. If I understand correctly, all your modeling assumes that you have basically, you might have a flaring disk that's basically a static disk, right? So how is the status here? Is there anything that you could speculate? What would go into doing a dynamical, I mean, a hydrodynamical time-dependent modeling? This is much shorter time scale than the evolution, right? Of these systems, and could you use that to do radiative transfer modeling and perhaps a time series or something?
Yeah, so the time series that I'm talking about, we have a time series of 6 years approximately time, and then we have seven different epochs, which means that the time these observations are taken are close enough in time such that the binary did not move enough. But these are all in observations with Pioneer and the near infrareds, and we see this only the disk inner rim, and we see that there is a change on those times on the inner rim structure, and this is very fast. So over the course of every single epoch already, actually. So yes, so the disk is not static for sure. We at the moment have not other such observations available to see if there is really a change in the target. How, except that we know that the binary moves, of course, so the binary stars are resolving around the center, common center of mass. For hydrostatic, for hydro simulations, I think this is a good next step as well to do this. And actually, we plan to use another radiative transfer code, which also can be coupled to the radiative transfer modeling efforts, and as such do radiative transfer and hydrodynamical modeling. Well, simultaneously is not the right word, but more or less simultaneously.
Yeah, that's nice. And then just a final question. This is also from my own interest in these systems. Two things which I believe, but correct me if I'm wrong, that you still have some issues with here is these things of the over residual flux component, right? And also this mysterious emission in the what we call hydro-Waller alpha line that you see, the static emission component, which I think you don't know where it comes from. If you were to speculate around those issues, what do you think? What is the missing component? Is there something significant that is missing here in terms of the current understanding of how these systems look, or is it some detail that it will be a technical issue to fix it, but it won't change any broader, so to say, interpretations?
So you were talking about the overresolved flux that's be constrained to be originating partly from the disk inner rim and partly from the positive side.
Indeed. And the other component that I was mentioning was this background static emission in the optical hydrogen bond, H alpha.
So, but that's coming from the jet actually, the H alpha.
The variation, yes.
The variations of
the
the H
variation,
alpha.
yes. But the static background component, does that also come from the jet?
I'm not an expert on the jets physics. I think these are two different studies going on. The characterization of the jets, the modeling of the jets, making ever more physical models of the jets. So for the for that one, yeah, there are radiator transfer modeling of the jet as well. But there is also components still missing that we need to explore the temperature of the jets, how the temperature changes over the extent, etc. It is so. I think these are two different studies characterizing the jets. However, the all-resolved flux component, yeah, could maybe also come from the jets somehow. But for this, we also need to know the temperature of the accretion disk around the jets way more robustly than we do now. So in that sense, they are also still coupled.
Thank you. Then we turn to the supervisors, whether they have still inspiration for questions or not.
Thank you. No, I have, it's very inspiring work, but I will not ask you any more questions. I just wanted to thank you and congratulate you on your very nice and clear presentation. And even though I already knew this results of your work, I'm still amazed when I see them again. So yeah, congratulations. I can only express also my congratulations. We will do that formally a bit later, but now I give the floor to the chair.
As this is a public defense, I should not forget to ask all of you whether there are still questions from the public. Please raise your hand if you still want to ask questions. Are there people online also?
Yeah,
Can they ask a question in the chat? Yeah, they don't.
Hi, Akke Corporaal, and I'll make this quick, but in our own solar system, we have examples where tidal forces can, for example, prohibit the formation of planets such as our asteroid belt. I was just wondering, if in a certain binary disk, we expect tidal forces from the binary to have a similar role.
I wouldn't know why not, to be honest. So I don't think that a circumbinary or circumstellar disk or a single star are different in that sense that they have no asteroid belts, that they would not have an asteroid belt, to be honest. So I would not see a reason why they wouldn't.
I guess I was thinking more generally just in terms of the prospect for planet formation at least. So like there's the short time scale, but on top of this, because if you require a binary in the middle, then you might expect just like with the orbital period and so on, that there are disturbing forces in the disk that might further prohibit the formation of a planet, for example. Or is this something that's been looked at before and found to be negligible? Or,
So this should be checked system by system actually, if this is actually a significant thing or not. In young stars, it doesn't seem to be a problem, I think, as far as I know from literature, although the binarity or even triple star systems can actually have a effect on the circumbinary disk for sure, or the circumstellar disk in any environment. For our systems, we know the orbital periods roughly, so we can check if this has an effect on the binary system, if it has an effect on the disk. For again the very typical full disk around the positive binary system, we did this computational with hydrodynamical simulations, and we found that the binary was not able to that the effect of the binary is very negligible. The dynamical truncation of the binary is within the cavity of the disk, basically. For other systems, we don't know. It could be also an explanation of the transition disk around positive binary systems, which is in some cases also an explanation for young stars, actually, that there is a large inner cavity which is created by some interaction, some binary interaction. So in that case, yes, this could have an effect on the evolution. If this has an effect on planet formation, that I don't know. Probably yes, but not further out. Probably in the inner regions, yes. but not further out.
Thanks.
Thank you. Anyone else who wants to ask a question? Good for my committee.
Hi, Akke. You did some fantastic work during your PhD, so well done. But so when it comes to plant formation, you mentioned that okay, time is an important factor for plant formation. Also, the luminosity is quite good. And in fact, those two things are quite well connected when it comes to post-HB evolution, meaning a lower mass, but a lower luminosity post-HB star will have a much longer evolutionary time scale. So, and in fact, yeah, when it comes to a lifetime of 10 to the 5 years is quite generous for most post-HB stars, but for post-RGB stars, this is not the case. Have you looked at the post-RGB stars in your sample specifically?
Yeah, so for everyone, so post-RGB stars are stars that went off the red giant phase and not after that phase actually. So they cut off their evolution from binary interaction lightly. There are a few systems in our sample that we believe are indeed post-RGB systems. We don't have, I didn't go that far to understand the exact differences between those systems that we know are post-RGB stars and those that we think are not. Also because we just don't know the exact distances and thus we don't know exact luminosity, so we cannot say exactly, well, for some systems we have an idea that they should be post-RGB systems, as you know, but for many systems we don't know if they are post-HGB or post-RGB objects.
So when you calculated the sublimation radius, and you also need the luminosity of the
Yes.
star, and I presume you figured it out from the interferometry?
No, so actually we did, most of the things are just not based on the distance. So yes, we took the distance from Gaia, from the Gaia mission. So these are astrometric observations, but only to have the absolute scales. All other things, that's why we plotted the inner rim radius versus the sublimation radius, because this is not dependent on any distance measurement or luminosity measurement, because it cancels out.
Thank you. Any more questions? If not, then the example team will leave the room for deliberation.
Better, huh?
Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the exam committee appointed for granting the doctoral degree in science, astronomy, and astrophysics. Akke Corporaal has presented to the faculty her PhD thesis on the topic infrared interferometric characterization of second-generation protoplanetary disks, impartial fulfillment of the requirements for a PhD in science, astronomy, and astrophysics. And she defended her thesis in a public session before the exam committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Akke Corporaal the degree of Doctor in Science, Astronomy, and Astrophysics. Congratulations, and I hereby close the session. Well done. And I now hand over the microphone to supervisors. I think they really want to get the last words as their supervisors.
Okay. Dr. As a promoter, I'm honored, always honored to be the first to call a former student doctor. So here we are, Dr. Akke. This morning you told me that you do not like to be the center of attention. Bad news for you, because we have two promoters and hence two laudatios, in which you are the center. So, sorry, you will remain a little bit out of your comfort zone a little bit longer. Laudatio means lofrede. So in I don't know the English word, praise, yeah, praise. And so it's not only one laudatio, it's two laudationes. So relax, but still. So 4 years ago, you entered our institute, and I thought to introduce you to all the people. I said, this is our new Dutch student, and that was already directly wrong, because you're not Dutch, but you're Frisian. And I think, apart from being an astronomer who combined all the instruments of the DFTI, you are also the first Frisian student of our institute, I think. So, well. It was 2019, I think, and then a few months later, or maybe 1 year later, we had the pandemic. But still, yeah, that's a difficult period, also for all students. It was also for us a difficult period, but you managed very well. And I think I want to thank you also for all your efforts in contributing to the social, to the mental health, because mental health is dear to you, and I think you've done a lot of effort to, with your contributions to team meeting organizations, of course, also from time to time a beer. That's also a good way of dealing with all the stress. And then organizing team meetings, yeah, contribution to GATKIP, you've been a buddy at IBS, and you co-organized a lot of social activities. So I think also probably the pandemic fostered you in taking a lot of attention to mental health, of which I would like to thank you, and in fact the whole institute would like to thank you for all your endeavors in that respect. We've talked about your scientific achievement, and I think Jacques will continue later on. And I would like to mention also here an anonymous referee report, because in the anonymous referee report, often you also learn quite a lot. And so the person wrote, the paper is well written, but the paper is well written and the modeling strategy is very well explained. Although the paper is perhaps a bit long. So that is also something we discussed a lot. The length of your text was always a matter of debate, let's say. But I think it's justified that the referee. So future papers by the author could, and probably should, refer to this paper as a benchmark and then make them more compactly. So I wish you, after your thesis, a lot of nice compact papers. Dr. Akke, Jacques will continue. And what comes next in your professional life is not yet clear. Of course, I wish you all the best. And whatever it will be, wherever it will lead you, I'm sure that your surroundings will be happy with a devoted and very talented researcher. And for this, I give the floor to Jacques to continue the debate.
Thank you, Hans. So as a co-supervisor, I had the honor to be the second person to call you with your title. So, dear Dr. Corporaal, what a pleasure to call you like that. And I'm joining Hans in congratulating you. It was quite a journey, and if I had to summarize it in one word, I would say complexity. Complexity because, first of all, your topic is actually at the intersection of several complex branches of astrophysics. First, binary evolution, where many phases are still to be understood, as they imply different physical processes, many of them explored at our institute. Second, radiative transfer, to describe how the energy is exchanged between all the different components of our system, and to understand what we are actually observing. And finally, a complex observing technique, infrared interferometry, that not only requires being able to combine the light from several optical telescopes with a micron-level precision, but also to transform the resulting interference patterns into something that a normal human being can understand. You are not a normal human being anymore, actually, as you can understand visibility plots just by looking at them and perform the Fourier transform in your head. Anyway, one can make a PhD in each of these topics separately. Mastering each of these pieces to assemble the post-AGB puzzle requires a lot of skills. At the same time, you have to react quickly, as during your defense, for example, learn and adapt to carry observational projects from writing, from proposal writing, observations with the largest telescopes in the world, so combining the 8-meter diameter telescopes of Parnell and pushing them to their limits, all the way to paper publication. I must say that for each of these steps, I very quickly was fully confident on your abilities to carry them successfully. Complexity also because you started in 2019. As Hans mentioned, you went through a peculiar times of COVID. So the impact of the virus was strong worldwide and also in our institute. And you developed to cope with that. Nevertheless, I will always remember happiness to attend the first live conference in Exeter in April last year, almost 3 years after starting your thesis. So congrats in making your PhD in times of COVID. It was not easy. Another source of complexity was that you had to deal with the disappearing of your co-supervisor during your critical stage of thesis writing. Well, looking at your thesis, you managed the stage very well, so it's a really great achievement. And did you really need your co-supervisor for that? But sometimes, I think that you enjoy complexity, especially when coding. During your thesis, you had to code to accommodate complex data compared to the outputs from radiative transfer codes, for example. And especially when starting your thesis, you wanted to write one script to solve everything at once. This resulted in a very complex code that had a great ability to hide any bug, such that finding it was, well, complex. While you undoubtedly do not fear complexity, and that is one of your strengths. I hope that I managed to convince you that sometimes simple is beautiful too. I could continue on mentioning other complexities. The point is that your PhD title you just obtained is of course reflecting your impressive scientific accomplishment and the technical skills that you acquired. But it is more than that. It proves that you are able to navigate through and deal with all the complexity with great success, without giving up, managing the associated stress, with a lot of enthusiasm and a great ability to learn, reflect critically, and constructively assess criticism to always improve. It shows that you can be confident in yourself to solve the most complex problems you encounter, regardless of them being in a scientific, professional, personal life, or coming from broader societal challenges. It was really a pleasure to work with you and accompany you on your PhD journey. I'm joining hands in wishing you all the best for the future. And the theme of complexity is reflected in the little gift that we have for you. So congratulations, Dr. Akke.
Joint gift from me.
You mentioned the puzzles of the post-stage binaries. So we got this way, like this one.
It's a mechanical model, mechanical model kinetic picture.
Show it to the camera.
Not really, I mean, I already mentioned it, but yes, it's really cool. Thank you. Okay, I guess it's my turn to say something. Yeah, so indeed it has been a very nice journey as well doing the PhD. Indeed, it has been governed by lockdowns as well, which was also super uncertain. That's yeah, Hans, Jacques, I really want to thank you for giving me the supervision that I needed, and I will actually keep it short. Maybe I will say something later as well, because I'm a bit out of words. So yeah, I will just. I also have something for you. And something for you.
Thank you very much.
Okay, so I think well, we can go to the reception and celebrate a bit more. Yeah, the reception is in Zaal Couvreur, which is around this building. Some people know how to compare, so please enjoy the reception as well.